Let us discuss about abnormal molar mass. We know colligative property depends only on the number of solute particles present in the solution. And through various colligative properties, we can calculate the molar mass of the solute. But with these formulae that is listed on top, we can calculate the molecular mass of solute exactly only for non-electrolytic solutions. For solutions which undergo dissociation or association, the number of solute particles will be more or less than expected, and hence the calculated molecular mass is higher or lower than the expected value. This is called as abnormal molar mass. Upon dissociation, number of particles increases, which in turn increase the observed colligative property. Since colligative property is directly proportional to number of solute particles, and we also know colligative property is inversely proportional to molar mass of the solute. So calculated molar mass will be lower than the normal value. For example, when 1 mole of KCl is dissolved in 1000 gram of water, number of effective particles present will be equal to 2 moles. That is 1 mole of K plus ions and 1 mole of Cl minus ions. The delta Tb for 1 mole of KCl will be equal to 0.52 Kelvin, and when it becomes 2 moles, the delta Tb value will also raise to 1.04 Kelvin. By knowing the other terms, molecular mass of KCl can be calculated, and it is equal to 37.5 grams per mole, which is half than the expected value. Thus, you can conclude molecular mass determined is lower than the expected one for dissociation. Upon association, number of particles decreases, which in turn decreases the observed colligative properties. We know colligative properties are directly proportional to the number of solute particles present, and we also know colligative property is inversely proportional to molecular mass of the solute. Hence, calculated molecular mass will be higher than the normal value for association. For example, when benzoic acid is dissolved in benzene, benzoic acid dimerizes due to hydrogen bonding formation. Dimerization means two molecules joining together, and they will resemble as a single molecule. Hence, because of dimerization, number of particles will get reduced to half. Now look at the calculation given on the slide. When molecular mass of benzoic acid is calculated based on depression of freezing point, its value is approximately double than the normal value. Thus, we can conclude when solute particles undergo association, molecular mass determined is higher than the normal value. In 1880, Dutch chemist Van 't Hoff introduced a factor represented using a small letter I to account for extent of ionization or dissociation. This Van 't Hoff factor I can be defined as observed colligative property divided by calculated colligative property. We know colligative property is inversely proportional to molecular mass of solute. So I can also be defined as normal molar mass by abnormal molar mass. We also know colligative property is directly proportional to number of solute particles. So I can also be expressed as total number of particles after association or dissociation divided by number of particles before association or dissociation. Let us calculate the degree of dissociation alpha. In a closed container, let us take 1 mole of reactant R. After some time, let us assume reactant R as dissociated to n number of products P, and the system has achieved equilibrium. At equilibrium, let alpha moles of product P be formed. So the reactant R remaining at equilibrium will be equal to its initial concentration, that is 1, minus number of moles of product form, that is alpha. So it will be equal to 1 minus alpha. Thus, by using the formula of Van 't Hoff factor, degree of dissociation alpha can be calculated, and thus alpha will be equal to I minus 1 by n minus 1, where I is the Van 't Hoff factor, n will be the number of particles dissociated. This formula is very important in examination point of view. Now let's calculate the degree of association alpha. In a closed container, let us take 1 mole of reactant RS. Let us assume after some time the reactant RS is associated to form the product RS to the subscript N, and the system has reached equilibrium. At equilibrium, number of moles of product form will be equal to alpha divided by number of particles associated, which will be represented as alpha by n, and number of moles of reactant remaining at equilibrium will be equal to initial concentration, that is 1, minus number of moles of product form, that is alpha. So it will be equal to 1 minus alpha. Thus, by using the formula of Van 't Hoff factor, degree of association alpha can be calculated, and it will be equal to I minus 1 by n minus 1. Then the entire expression will be multiplied by number of particles n. These are the key points to be remembered when the solute particles undergoes association or dissociation. Due to the inclusion of Van 't Hoff factor I, the colligative properties formula will get modified as follows.